Vanakkam. Welcome to this course on biomedical instrumentation. We have been looking at pressure measurement systems. We looked at direct pressure measurement using intravascular or catheter tip based systems, and we gave some specific examples also. We discussed a very specific system in terms of the piezo-resistive system, and we discussed the advantages and disadvantages. If you recall, what are the advantages? High fidelity, high accuracy and very high or flat frequency response, rapid measurement. What is the disadvantage? You are essentially having a trade-off between the material property, its flexibility and its durability. We continue our discussion on pressure measurement, but we take a detour into a different topic. So, in this video, we look at other sensor technologies for measuring pressure. Specifically, we look at extravascular systems, extravascular sensors. What are the key components of an extravascular blood pressure measurement system? Specifically, the fluid filled catheters. What is the working principle of a fluid filled catheter? What are some critical design considerations in using a fluid filled catheter to continuously measure and monitor blood pressure? Catheter orientation and reference level are some of the critical considerations. So, some of the other sensors that may be used in blood pressure measurement are piezoelectric sensors. We looked at what is piezoelectricity. Piezoelectricity is this property in which some specific materials show a change in potential in response to a stress, mechanical stress, right. This is quite common in other fields. These are excellent for measuring transients, but not really so good for measuring static applications. So these are AC coupled sensors, so they really cannot measure mean pressure or average pressure. So these are only useful for capturing transients or fast time varying pressure signals, and not useful for blood pressure monitoring in a case where the pressure is going to remain approximately constant or change relatively slowly. In such cases, piezoelectric sensors are not really the modality of choice. The other option is surface acoustic wave sensors or the SAW sensors. These are relatively simpler, they are low in power and they are quite stable over relatively longer periods of time, especially when you provide appropriate compensation for changes in temperature compensation. What this does, the principle of operation is that it detects changes in the resonant frequency of the diaphragm, usually the piezoelectric diaphragm, as the diaphragm deforms. Now, it is still not practical in measuring blood pressure, but seems like a promising avenue for future research, especially in implantable devices similar to capacitive sensors. So, something that we can implant and forget it for a very long time. And the last is fiber optic sensors, which can be extraordinarily tiny, really small. And the other advantage, of course, with the light sensors, optical sensors, is that these are immune to electromagnetic interference, can also be used in MRI sensitive systems, can be useful in sensitive environments. So, these function by reflecting light off of a deformable diaphragm. So, depending on the pressure, the light changes the interference patterns. And earlier there were challenges with drift, because these sensors have, when there is a constant application, there will be a drift, for example, this sort of this. So, earlier they used to have challenges with the reliability of blood pressure measurement. Now these are also being addressed. These are some of the other sensor technologies that are available for measuring blood pressure. The other technology, the other method for measuring blood pressure is using extravascular sensors. What are extravascular sensors? These are those that measure blood pressure by using a fluid filled catheter, and the measurement itself is done outside the vascular system. That is what is the extravascular. Extra means not more, extra means outside, vascular means vascular, outside the vascular system. What is the disadvantage of this? Obviously, you need to have a method that will faithfully transmit the pressure changes to outside. Actually, that is actually a relatively straightforward procedure, because it turns out this is essentially a principle of hydrostatics. It turns out that pressure that is applied on a fluid is transmitted equally in all directions. So, one component of that pressure will also be detected in the fluid filled catheter. So, the actual pressure sensor can be one of these, it can be a strain gauge, can be an inductance, can be a capacitance, or an auto electronic or a piezoresistive piezoelectric sensor that is kept outside the vascular system in the fluid filled catheter. It is commonly used in intensive care units, more common in intensive care units and in surgical settings for continuous blood pressure monitoring. What are the challenges with this system? The challenge is that it requires frequent flushing, frequent zeroing. We'll get into it in a bit. What are the key components of this system? Essentially a catheter, which is a thin flexible tube, can be as thin as, for example, the 1.67 mm we discussed. That is inserted into an artery or a vein, and this tube is filled with specific fluid, not any fluid. It is filled with saline heparin solution. What is the function of chemicals like heparin? Check this. Google about this. Heparin, warfarin. What do they do? Their purpose is to prevent clotting. This is a common problem when you introduce an external agent into the cardiovascular system, into the vascular system. There is a possibility of an introduction of clotting. There is a possibility of formation of a thrombus. There are some serious consequences of this. So, heparin solution is used. Heparin is a chemical that prevents clotting. So, heparin solution is used along with saline in the catheter, and there is a three-way stop clock that allows for sampling of the blood and frequent zeroing of the sensors for accurate measurement. So, it turns out that every once in a while you will have to zero that, otherwise there will be a drift in that. And you can use a disposable pressure sensor at the tip. This pressure sensor detects the transmitted pressure at the extravascular end, at the outside end, and converts it into an electrical signal which we can then read and then display, for example. And then there is a flush device that essentially ensures that the catheter remains open by preventing clot formation, because if a clot forms, clot is solid and the catheter itself contains only fluid. So, any pressure change at the intravascular end of the catheter will not be detected at the extravascular end. So, we will have to ensure that the catheter is open and patent, and it does not have any clot that is obstructing or any other solid that is obstructing. The other possibility is the formation of bubbles, for example. What is the principle of operation? So, you essentially insert a catheter into a blood vessel using a small incision to expose the vessel, and then insert the catheter through the vessel. The other is percutaneous insertion. In this case, you use a special needle or a special guide wire to insert without actually performing a cut with a knife. and blood pressure essentially applies force on the liquid column on the inside part of the catheter, inside the catheter, and this force is then getting transmitted along the liquid column to the extravascular pressure sensor diaphragm, which is going to detect this deflection. And this deflection of the diaphragm is then converted into electrical signal, either using capacitive system or using strain gauge system or using piezoelectric system or using piezoresistive system, one of these changes which detects essentially the change in the deflection, displacement. It is quite useful in monitoring for long time, continuous monitoring, and you can recalibrate quite often. You must recalibrate quite often actually, because there will be drift in this system. So, also one more thing is to make sure that the flush device stays open, that is the flush device is used to make sure that the catheter remains open and patent. These are the principles. Make sure that the catheter is able to detect pressure on the outside end. What is the major disadvantage? The disadvantage is that it is going to take time for the pressure signal to travel from the inside end of the catheter to the outside end of the catheter, depending on the length of the catheter. That is not the only disadvantage. The other disadvantage is catheter property, material property of the catheter will affect changes in the pressure. So, catheter design itself will affect measurement of the pressure. Essentially, what is the principle? The internal pressure, the pressure that is on the inside of the system, inside of the intravascular pressure, is hydraulically transmitted via a column of saline and heparin along a flexible catheter to the outside. For example, that outside sensor might be a strain gauge Wheatstone bridge system. Now, this fluid filled catheter plus sensor essentially behaves like a mass spring damper system, which is mx double, whose governing equation is mx double dot plus cx dot plus kx is some applied force f of t, where we know what is m, what is c. M is the mass of the fluid, c is the viscous resistance, and k is the elastance, it is the property of the sensor chamber. Rho and eta are respectively the density and the viscosity of the fluid, and R and L are the radius and the length of the catheter, and K is the constant that relates the pressure and elastance. So, we know its natural frequency. It is not rocket science to know this, but if you do not know how to arrive at this, please do check this, what the natural frequency and the damping ratio of this system would be. So, what we can say is that, without going into the details of how this system behaves, is that a higher natural frequency and moderate damping ratio essentially makes sure that fast waves are properly preserved and measured. But if you have very long length of the catheter, or if the radius of the catheter is too small, then it essentially reduces the natural frequency and raises the damping ratio, thus reducing the ability of the system to measure sudden changes. Sharp transients will not be measured if the length is too long and or if the radius is too small. So, essentially the frequency response is dependent on the catheter characteristics. I already mentioned this. If you have a longer tubing or thinner tubing, that will reduce the natural frequency essentially and increasing the damping, causing loss of sudden changes. But you are interested in measuring sudden changes, then in that case you have to have a thicker catheter. Well, if you have a thicker catheter, it is more difficult to insert that, right? You need a bigger artery or a bigger blood vessel to insert it into, for example. So, not all of these are solvable. For example, these are the multiple challenges that you have. These are the trade-offs that you have. If you have a bigger catheter, you are going to have better frequency response. You are going to be able to detect faster changes. That's good. But if you have a bigger catheter, that also means the risk of sending it through a smaller blood vessel is higher, or you need to locate a different blood vessel that can host this catheter, etc. So, there are challenges. One more challenge is the so-called whip. This is the catheter whip artifact, in which case sudden changes of high velocity blood flow sometimes causes oscillations of the flexible catheter, which are reflected as pressure changes in the extravascular sensor. But this is just noise, this is an artifact. This is not actual pressure change, but rather a high velocity blood flow that happened once that causes oscillations that are measured as oscillation of the pressure itself on the outside. This can be identified by using this characteristic ringing pattern on the trace. There will be frequent changes of this pattern. Another challenge is the challenge of orientation. When you measure physiological pressure like blood pressure or venous pressure, absolutely critical to decide where you will place the catheter. The position of the catheter and the transducer absolutely matters, because gravity affects blood pressure inside the body. For example, if you have a water tank, the pressure at the top of the tank is much lower than the pressure at the bottom of the tank. Why? Because that's how it is, because of gravitational potential energy. So, to appropriately measure blood pressure, usually the right atrium is chosen as the standard reference point. Recall, in one of our first videos, I mentioned that the standard reference point for measuring blood pressure is the fourth intercostal space along the mid segmental line. Is it not? We discussed this in one of the earliest slides. This is perhaps the most posture independent location. That means regardless of whether the person is lying down supine or sitting up, the pressure change will not be much. Anatomically, it aligns with the fourth intercostal space of the mid-sternal line. I said mid-segmental line. That is essentially the fourth intercostal space of the mid-sternal line. Why to use this as the reference? So that we can measure pressure values that are of interest to us. So, to make sure that the position of the sensor does not affect pressure readings across patients and across settings. So, to eliminate any changes or variations in pressure values, and to make sure that recordings are consistent across patients and settings. So, there is this hydrostatic pressure. As you move up or down, gravity causes pressure to change. That change in pressure is essentially rho GH, where rho is the density of this fluid. In this case, blood has a density of 1055 kg per meter cube. A small change of approximately 1 centimeter in height essentially causes a pressure change of about 0.74 millimeter mercury. This means that if the pressure transducer is placed too low, then it will add hydrostatic pressure. It is like you are measuring the pressure of water at the bottom of the water tank. Okay. This will inflate or increase the pressure readings. Or if you place the sensor too high, then it will reduce the hydrostatic pressure. This is like measuring the pressure at the top of the tank, water tank. This will artificially reduce the pressure readings. So, to make sure that you get accurate readings of pressure, especially the central venous pressure, we must ensure that the pressure transducer is placed at the level of the right atrium. This will help us measure what is of interest for us. What is of interest for us? We are interested in measuring the central venous pressure, the CVP. and this CVP is the pressure in the central vein that is close to the right atrium. This essentially reflects how much blood is returning through to the venous system. What is the elasticity of the veins? What is the intrapleural pressure? That is the pressure in the thoracic cavity, intrapleural pressure, and the performance of the cardiac system, the cardiac performance. Note that the central venous pressure increases when heart function deteriorates, for example. This is critical because CVP is often monitored in ICUs to ensure that cardiac function is intact and fluid status is proper. Another thing that affects, previous slide we looked at the potential energy characteristics. What also happens is, because blood is flowing and flowing with some non-zero velocity, there is also a kinetic energy, especially when it flows through large vessels. When blood flows fast through large vessels, there is a kinetic energy that can also affect pressure readings depending on how the catheter is oriented, and this is something that we can model. So, the total energy per unit volume is essentially the static pressure plus the potential change, or the potential energy, or the change in the potential energy and the kinetic energy. So, from all this discussion we could come up with a simple description of how to use an appropriate reference level in measuring blood pressure and catheter orientation. If the tip is facing upstream, then the total pressure is being measured and usually it reflects a higher reading. If the catheter tip is facing sideways, then it essentially measures the static pressure and it is almost always the most accurate measure. If the tip is facing downstream, usually it is not very stable, highly unstable, there are oscillations. It is usually close to side pressure but can vary a lot. So, how you place the tip absolutely matters, right? How and where you place the tip matters a lot. So, with this we come to the end of this video. In this video we looked at other ways of measuring blood pressure. We looked at SAW, we looked at piezoelectricity, we looked at optical systems, we looked at extravascular sensors, what are the key components and working principle of fluid filled catheters. We looked at the various considerations, design considerations, and how catheter orientation and reference points, reference level plays an absolutely critical role in measurement of pressure in this extravascular blood pressure measurement system. With this we come to the end of this video. Thank you very much for your attention.